In this last problem, we're going to put it all together and do the sum of all the torques and use Newton's third law for torques, or sorry, second law for torques, and find out if this person will cause the plank to rotate. So a torque is given by R times F times sine of phi, and Newton's law of torques is the sum of all the torques is equal to for equilibrium is equal to 0 because we don't want it to move. So we have to draw our plank. We have Adrienne, which we're going to make a green. Our person here at the edge. We have our first balance here, 2 meters away. Then another balance, 3 meters away. And then the total distance remaining is 4 meters. So our beam has a total distance of 4 plus 3 plus 2, so that's 9 meters. So that means the center of the beam is at R equals 4.5 meters. And then we have another person here at some unknown distance, and how far can they go? So we have to find that distance. So we have a lot of forces going on here. The first thing we have to do is pick a point in which we're going to rotate. You can pick any point you want for this rotation to happen, but an obvious choice to make your life easier will always be picking one of the support beams. So I want to pick this one as our point where R equals 0. So we're defining our origin. So that means we have one force from the person on the left. Their gravitational force is going to be downward. So let's draw our forces. The gravitational force, well, let's use green. Or let's draw our beam. So we have a green force at the edge going down. This is their gravitational force from the person on the left. We have our first support force, normal force, going up. Then we have at the center FG of the beam. Then we have the support force of the second support. So I'm zooming in so that it's easier to see. And then we're going to use blue, the gravitational force of our final person. So we have 5 forces. And we have to find all of them. So let's find the distances between these forces. So for the green, R is 2 meters. The distance from our pivot point, which we chose to be at the first support, to the green force is 2 meters. For this guy here, R is 0 because we picked that to be our pivot point. The distance to the gravitational force of the beam is, the center of the beam is at 4.5 minus 2. So that is R is equal to 2.5 meters. Then this normal force has an R here of 3 meters. And then this guy has an R, let's use blue, and that is our unknown. So in order to find the normal force, this is also unknown here. This one doesn't matter because the torque here is going to be 0. So we don't need to find that normal force. But we have to do the sum of all the forces and the sum of all the torques. So the sum of all the forces in the y direction is equal to 0 because we're in equilibrium. That is equal to Fn1. So let's label these 1 and 2. Fn1 plus Fn2 minus Ma, where A is the green, times G, because their person's name is Adrienne, minus M of Beau, G, minus capital M, G, where capital M is the mass of the beam itself. And this is equal to 0. We also have to write down the sum of all the torques is equal to 0. So our torques are we have this torque. We have to define our coordinate system in the same way. If Fy has an up and down, we have to define torques clockwise and counterclockwise as positive and negative. So this torque, the green torque, is going to cause a clockwise movement, whereas everything else will cause a counterclockwise movement, right? This one will cause it to go this way. This one will cause it to go this way. But Fn2 will cause it to go clockwise. So torques for Fn2 and the green need to be considered positive, whereas Fg that's in blue and the gravitational force of the beam itself cause negative torques. So let's use our colors. We're going to say MAG times the green R that's positive. Our other positive one is Fn2 times that R, which is 3. Those are positive. And remember, the phi's for our sine are all 90, so they go away, which is great because we don't want angles in this. Then we have our blue minus MB G times the blue R, which is our unknown. And then we also have minus capital M G times this R here, which is 2.5 for the center of mass of this. And this is all equal to 0 because it's not rotating. So we have 2 equations and 2 unknowns. So at the tipping point, the first torque, or the point here, will no longer have a normal force. So that means that Fn1 has to equal 0. So Fn2 minus MAG minus MBG minus capital MG equals 0. So Fn2 equals MAG plus MBG plus MG, which equals, let's factor out the G, MA plus MB plus capital M. So that tells us our normal force for our other equation. So if we go to our torque equation, we want to solve for the blue R. So MA is given, this person weighs, go back. MA is 50. MB is 90 kilograms. Kilograms. And capital M is 100 kilograms. So MA is 50. G is 9.8. R is 2 meters. And this is all from the green. Then we have plus FN2, which is G times MA plus MB plus capital M. That is times FN2, where its R is 3, so times 3. And then we have minus MB 90 times G. Let's do this, 9.8 times the distance there, which is our unknown blue R. And then we have our final one, which is minus M, which is 100 times 9.8 times the distance to the center, which is 2.5. So this is the blue, this is F2N, and this is MG. So if we plug all of these guys in, to our lovely calculator, 50 times 9.8 times 2, this is 980 plus G 9.8 times MA 50 plus MB 90 plus M 100 times 3. This is 7056 minus 90 times 9.8. 882 times our blue R minus, minus 100 times 9.8 times 2.5. 2450. That equals 0. So 980 plus 7056 minus 2450 equals 882 times blue R. So 980 plus 7056 minus 2450, that's, not erase, 5586 equals 882R. Blue R. So that means that blue R equals 5586 divided by 882, which is 6.3 meters.